Okay, today we're going to be talking about 2.5, which is the transformations of functions. They're going to go over some of your basic functions here. The constant function, that's if you have f of x is equal to some constant c. The domain of this is negative infinity to infinity because it's going forever in both directions. The range is just whatever that c value is because it's that way all the way across your y. And it's even because it's reflected across the y-axis. The identity function, that is f of x is equal to x. Again, negative infinity to infinity for your domain because it's going forever in both directions. Same is true for range in this case because it's going up and going down, right? Increasing on, I skipped this over here. It's constant from negative infinity to infinity here because it's staying the same. This one is increasing from negative infinity to infinity because it's always traveling up. We always read it from left to right. And it's an odd function because it has symmetry over the origin. On this one, this is the parent function for the absolute value. And it also has a domain of negative infinity to infinity because it's going in both directions. Its range, however, starts at 0 and it's going up, right? So it's it's 0 to infinity. And then it's decreasing from negative infinity to 0, and then it's increasing from 0 to positive infinity. And it's even because it reflects over that y-axis. Okay, very similar here for your quadratic. All essentially is the same as your absolute value. Square root function looks like this. On this, we have a domain starting at 0 and it's going towards the positive numbers, so it's going to infinity. Range is the same, starts at 0 and it's moving up above, so it's going to the positive numbers for y. It's increasing from 0 to infinity, and it's neither even or odd because there's no symmetry for this function. The standard cubic function, which is f of x, is equal to x cubed. Domain is negative infinity to positive infinity because it's going in both directions. Range is the same thing, it's traveling down and up, and then it's increasing the whole way through, so negative infinity to positive infinity. And it is an odd function because it reflects over the origin. The cube root is also similar to your standard standard cubic function. F of x is equal to the cube root of x. So your domain, again, is traveling left, it's traveling right, so negative infinity to infinity. Range, it's going down and up, so same thing there. And then it's also increasing this whole time. So it's increasing across the whole thing, and it's odd because it has a reflection over that origin. Vertical shifts, basically what this is saying is if you have this parent function of f of x is equal to x squared, and I add 2 to that, to get g of x, I'm taking that original function and adding 2. That's going to shift it up 2 units. I could do the same thing with that same function and subtract 3. This is going to give it a vertical shift down 3 units because I'm subtracting. So whatever I add or subtract to the end of that parent function, that's going to give us a vertical shift. So let f be a function and c a positive real number. The graph of y equals f of x plus c is the graph of y equals f of x shifted c units vertically upward. And then same thing, if it's being subtracted, it's being shifted downward. So the parent function they're saying is this, and if you're adding c to it, it's going to move every point on that function up, that c, that constant. Same is true if this was the parent function and you were subtracting c, every point on that function is going to go down c units. Okay, so use the graph of the absolute value of x to obtain the graph of the absolute value of x minus 4. I should have put a coordinate plane in here. So it looks like this, right? And if it's minus 4, we're going to be shifting down 4 units. Okay, it's a vertical shift down, so 1, 2, 3, and 4. And everything is just going to be, I'm not going to be able to do this because I'm on my tablet. I missed. Okay, so everything just shifts down 4 units. Horizontal shifts. If it's a horizontal shift, it's going inside of those parentheses, for example. So you're actually taking x minus 3 quantity squared. So this is, if you're talking about the parent function, f of x squared, and we are moving it left or right, we have that plus or minus inside of those parentheses. The only thing that you really have to be careful on these is if you are subtracting on the inside, you're actually moving to the right. Okay, so if you're subtracting here, your horizontal shift is to the right. If you are adding, your horizontal shift is to the left. So it's kind of backwards from what you might think. Okay, so this is, does it seem strange that subtracting 3 causes it to shift to the right, and then it actually has you do the math to figure out why? So it does work. So same thing as before, if you're adding a constant inside, it's a left shift C units. If you're subtracting it for that horizontal shift, you're shifting to the right C units. So, for example, use the graph of f of x is equal to the square root of x to obtain the graph of g of x, is equal to the square root of x plus 5. So if I'm adding inside here, that means it is a horizontal shift and it's adding, so I'm going to move to the left. So whenever I do this, my square root function looks like this. And if I'm moving everything 5 units to the left, 1, 2, 3, 4, 5, it goes like this, right? It should look exactly the same. It doesn't, but it should. On a test, I would want to see 2 or 3 ordered pairs, and then I would want to see those same ordered pairs translated over. So some functions can be graphed by combining horizontal and vertical shifts. These functions will be variations of a function whose equation you know how to graph, such as the standard quadratic function, cubic function, yada yada. In our next example, we will use the graph of the standard quadratic function f of x equals x squared to obtain h of x is equal to the quantity of x plus 1 squared minus 3. Okay, we'll graph 3 functions. We'll start by graphing the parent function, then we're going to shift it horizontally, and then we're going to shift it vertically. So the parent, horizontal, and then vertical shift. So, again, I should have put myself some coordinate planes on here. Alright, so the parent function looks about like this. Pretend it hit the origin because it should have. My horizontal shift is what's happening here. If it's plus 1, that means I'm going to move left everything 1 unit. I'm going to change the color of my pen for this. Okay, so blue, moving left. So everything is just going to move over 1. So basically looks like this, right? And then I'm going to do my vertical shift, which is this part. If I'm subtracting for the vertical, I'm moving down. So I'm going to go 1, 2, 3. So in this case, my vertex is going to be right here. And I'm just taking that whole thing. Oh my lord. And I'm moving it down. Pretend like those look like real parabolas, because they're supposed to be. Alright, if it's reflected about the x-axis, that means that the graph of y equals negative f of x is the graph of y equals f of x reflected about the x-axis. So use the graph of f of x equals the cube root of x to obtain the graph of g of x equals negative cube root of x. Okay, I decided to go ahead and get myself some coordinate planes so that I could do this more effectively. So, on this one, our cube root function, the parent function for that, it goes through 8, negative 2, or excuse me, -8, -2, 0, 0, and 8, 2. And so it looks like this ish, right? And then if we are doing a reflection about the x-axis, what's going to happen to those points is they're just going to switch spots. So they're going to flip right over the x-axis, which is here. So instead of being -8, -2, it's going to be -8, +2. 0, 0 stays the same because if you change the sign, nothing happens there, right? And then it's going to be +8, -2. Okay? So it looks like this. Okay, reflected about the x-axis. Similarly, if you have the negative on the inside, that's going to be reflected about the y-axis. Okay, so on example 5, they say use the graph of the square root of x to obtain the graph of the square root of -x. So on this one, we go through 0, 0, 1, 1, and 4, 2. 2, 3, 4, 2. Okay, so it goes like this. Okay. And if it's negative on the inside, I'm going to flip it about the y-axis, excuse me. So I'm going to go 0, 0 again, isn't going to change. Instead of being 1, +1, it's going to be -1, +1, because we're flipping about the y. So in this case, our x values are what's changing. And this one, it was 4, 2. This one's going to be -4, 2. So it looks like this. Okay. So again, on a test, I would want to see 3 specific points, and for you to tell me what those are whenever you've shown that translation. Vertical stretching and shrinking. Excuse me, I like this definition better. A lot of blah 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 there. Okay, so let f be a function and c a positive real number. If c is greater than 1, the graph of y equals c times f of x, so you're multiplying it by that function, is the graph of y equals f of x vertically stretched. Okay, so it's actually going to get skinnier. Okay, so it's stretching it, it's elongating it, it's making it longer. Okay, and you can do that by multiplying its y coordinates by c, so whatever that constant is. If it's between 0 and 1, that's what this is saying, a number between 0 and 1 would be a fraction. Okay, so basically what this is saying is if it is a fraction, it's the same thing, but it's a vertical shrink, which means they're making it shorter. So the parent function on these is right here. Oh, I missed the mark on that one. Okay, so see, the parent function is the same on both of those. However, whenever c is greater than 1, it's a stretch. It's making it taller. When c is between 0 and 1, otherwise a fraction, it's making it shorter. Okay, do you see that? Hopefully you do. So use the graph of of f of x equals x cubed to obtain the graph of h of x equals 1/2 of h cubed. So first of all, this is between 0, oops, this is c, not x, and 1. Okay, so that means it's going to be a shrink. So it's smashing it down. So the parent function for this one goes through -2, -8, 0, 0, and 2, +8. So it looks like this. Okay, so the way I do this shrink, or the vertical stretch as they call it, is I'm going to take my y value times that c. Okay, so on this one, my -2 doesn't change, but instead of it being -8, I'm going to take -8 times 1/2, which is -4. So -2, 1, 2, 3, 4. It's right here. It's really hard to see this with my poor sketching skills on these. Okay, same thing here. 0 times 0 still gives me 0. 2, 8 is instead going to be 2, 4 right here. So this one is right here, which looks like it's the exact same, but it's really not. I just have really bad handwriting skills. You can do that on your calculator to be able to see the actual graph difference. Okay, so this is similar to that vertical shrinking or stretching, okay, except for it's horizontal, and in this case, you have the constant being multiplied on the inside there. So if it's on the inside, not multiplied on the outside times the whole thing, but just on the inside there, by x, if it's greater than 1, it's going to be horizontally shrunk. So it's going to be compressed inward, okay? If it's between 0 and 1, which we talked about a few minutes ago, that's a fraction, right? And if it's between 0 and 1, in this case, it's going to be horizontally stretched, okay? So again, your parent functions are right here. This is the same parent function for both of these. But on this one, it's being shrunk because what's on the inside is greater than 1. Okay, the C value is greater than 1, so they're shrinking it in horizontally. If it's between 0 and 1, which is what's happening here, oh my gosh, I highlighted the wrong thing. Yeah, I did. This is supposed to be the parent function. Sorry. I got carried away. This one, the second one, is the parent function. And it's being stretched out to the other. Okay? Alright, so on this one, it says use the graph, which is what I've given you there, to obtain each of the following. So the first one is f of 2x. So right here, it's on the inside there, so it's going to be a horizontal, which they tell us in the example here. It's a horizontal stretch or shrink. If it's 2, that's greater than 1, which means we're going to have a horizontal shrink. So what you're going to do is you're going to take each x coordinate and you're going to divide it by 2. So this one is -4. So -4 divided by 2 is -2. I'm just going to move it in right here. Oh, I wanted to change colors though. Okay, so -2, the 0 doesn't change. This one was -2. Divided by this 2 is going to be a -1. The y coordinate, again, doesn't change. 0 isn't going to change. 0 divided by 2 is just 0. This one is 2 divided by 2 is going to be a 1. 4 divided by 2 is 2. So the y value doesn't change. I'm not moving up or down. I'm just making it, or I'm just changing the x coordinates. Okay, so that's what I have for that one. On the next one, change my pen again here. I want to find f of 1/2 of x. So what I'm going to do is essentially the exact same thing. I'm going to take, for this original, the purple, which is the original, I'm going to take the x coordinate and I'm going to divide by 1/2. Well, when I divide by 1/2, I hope you remember that that's the same as multiplying by 2, right? Because I'm multiplying by the reciprocal. So on this one, instead of it being 4, when I divide by 1/2, I multiply by 2, it becomes 8. This one was 2 times 2 is now 4. Again, 0 doesn't change. This one was 2, so now it becomes 4. This one was 4, so now it becomes 8. So I have this. We'll pretend like those are straight lines, okay? So that's how that horizontal stretch and shrink works. Okay. A function involving more than one transformation can be graphed by, excuse me, by performing transformations in the following order. So the order matters, okay? We want to horizontally shift first, then we're going to shrink or stretch, then we're going to do any reflecting necessary, and then finally any vertical shifting. So on example 8, it says to use the graph of the given, that was the same. I put it in on this one, but not on the next one. So what we're going to do is we're going to put these in here real quick 1, 2, 3, 4, I think is where it was. 0, or not 0, negative 2, 4, 0, 0, 2, negative 2, and 2, 0. Okay, so parent function, same starting point as the last one. And they're having you do this with this random thing, so you actually have to practice the tools, okay? So the first thing we're going to do is this any horizontal shifting. So do we have any horizontal shifting? We look inside of here. Do I? The answer is yes. Okay, if I'm subtracting by 1 on the inside, that means I'm going to do a horizontal shift to the left. So every point is going to move 1 to the left. Okay? Or excuse me, I said that wrong. To the right, because it's backwards. See, even I still mess that up sometimes. Okay, so negative, it's the opposite of what you think on your horizontal. It goes to the right. So every one of these points is going to go to the right. So right 1, right 1, right 1, right 1, right 1. So at this point, this is what I have. Okay, so the next thing I'm looking at is 2. Do I have any shrinking or stretching? And I do, because I have, let me change my pen color again. I do because I have this 1/2 out in front, right? So whenever I have that shrinking or stretching, what I'm going to do is, in this case, 1/2 is the fraction, so it's going to be a vertical shrink by a factor of 1/2. So what I'm going to do is take every y coordinate and multiply it by 1/2. So if I take 0, because that's what the y coordinate is here, right, times 1/2, I still get 0. So that one doesn't move. This one is 4 times 1/2 is 2. Again, 0 doesn't move. Negative 2 times 1/2 is negative 1. 0 doesn't move. So now this is my new function. It's getting hard to see on all these on top of each other. Okay. The next thing I have is any reflecting. So do I have any reflecting? And I do, because of this negative out in front. So what that negative tells me I need to do is just flip every point over the x-axis, okay? Because that negative out front means that I'm reflecting about the x. So I'm going to take, this one doesn't move. This one, instead of being negative 1, 2, becomes negative 1, negative 2. This one doesn't move. Instead of being 3, negative 1, it becomes 3, positive 1, and this one doesn't move. So I have this right here. So the green is my new current. And then lastly, I have any vertical shifting. So vertical shifting, remember, is if I'm adding or subtracting anything to the end. I don't have a great color to, I'm used to black, I guess. And I do have some vertical shifting here. I have that plus 3. So what I'm going to do is I'm going to take every point and I'm going to move it up 3. So I have 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. And 1, 2, 3. So I have this black is my last function that I end with. So that's my final after I do all 4 of those shifts. Okay, so use the graph of f of x equals x squared to graph g of x equals 2 times x plus 3 quantity squared minus 1. So on this one, I'm going to start with my parent function for the parabola. So a parabola we know goes through 0, 0, negative 1, 1, and let's say negative 2, 1, 2, 3, 4, 1, 2, 3, 4. I'm never going to hit all 5 of those points. Let's go 3, 1, 2, no, 4, 5, 6, 7, 8, 9, 9. Okay, so Now, you don't have to, look how, that's pretty good, guys. Okay, you don't have to have as many points as what I have here. I need 3 quality points. Okay, I just did that so I could draw a better function, okay, make it look more accurate. So on this, I'm going to follow my same process. So the first thing I want to do is any horizontal shifting. Remember, horizontal, I find on the inside there. So I have this +3. Remember, on the inside, horizontal shifting, it's backwards from what you think. So instead of going to the right 3, we're going left 3. So all of these points are moving left 3. So 1, 2, 3 right here. 1, 2, 3 right here. 1, 2, 3 here. 3, 3. So I have this. Not as good. Not as good. Can't do it. Can't do it twice. Okay, next, any stretching that I have. In this case, I have, change my pen color. In this case, I'm stretching by 2. So what I'm going to do is I'm going to multiply each y coordinate by 2. So I'm not going to be able to do these bigger ones, right? Because if I take 9 times 2, it's way up here. So if I do, this is 4. So 4 times 2 is 8. 1, 2, 3, 4. Gives me 8 right there. This one is a 1, so times 2 is 2. 0 times 2 is still 0. This one's going to move up here. This one's going to move up here. So you can see that I had that vertical stretch, okay, by a factor of 2. You can tell it's skinnier from that purple function. The next thing on this one, I've done my horizontal, I've done my stretching. I only have one thing left because I don't have any reflecting because it's positive. So my last piece on this one is just this vertical shift. And what I'm going to do is I'm just going to take every point and move it down 1 unit. So this one comes down here, this one here, this one here, here, and here. So it looks like this. Okay, so that's my final answer. And this is your assignment for today.